Hello everyone. Thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Numerical Solutions of Nonlinear Equations, and it is going to introduce useful methods to solve these equations. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the Newton's method and the second method before wrapping up with conclusions. Now we will give a brief introduction for numerical solutions of nonlinear equations. The problem setting is the following. We are given a function f of x. It is a continuous function and real valued and possibly nonlinear, because we know if fx shall be a linear function, then finding the root is trivial. So we want to find the root for this function, such that at the root the function admits 0 as its value. So this is the same as solving the equation f of x equals to 0, where the f is a nonlinear function. Before we get into any algorithms, let's take a look at some simple examples, just to warm up. For first example, let's take a familiar quadratic polynomial as our own function. It is x squared plus 5x plus 6. So we all know how to factorize a quadratic polynomial, and this will give you x plus 2 times x plus 3. And finding 0 is easy. We find actually two roots. One is -2, the other is -3. So this example shows to us that for a nonlinear function, the roots are not unique. There can be multiple of them. The second example, still a quadratic polynomial. Let's see, I have x squared plus 4x plus 10. You see, you can only make the first two terms a perfect square by adding a constant, for this gives me x. The housing square plus what remains is 6. So this function here is always bigger than or equal to 6. So it will have no roots. This example shows the case that nonlinear functions might not have any roots. The last one, this is a silly example. So I'm just writing a horrible nonlinear function, throwing any random terms, and I want you to find its roots. However, the point I want to make is that this is not. Think of any function nonlinear taking some expressions. There might not be an exact expression for the root. So the comments here will be roots can be difficult, or maybe even impossible to find analytically. If there shall be the case in general, then having a numerical algorithm that will generate an approximate solution would be very useful. Next, we will learn the Newton's method. Our goal is that given a continuous function f of x, we want to find the root, such that f of r equal to 0. So the main idea behind Newton's method is the following. Given an xk, we guess at step k. The next guess xk plus 1 is achieved by approximating your function f as a linear function at xk. Then we all know a linear function is very easy to solve. And you solve it, and that solution will be the xk plus 1, your next approximation. Here is a graphic illustration of the method. Let's say this is your xk at that point, and your function value that xk takes that value. So what I do is at that point, I draw a tangent line to the curve of the graph of f, which is this red line here. So this is called a linearization of f at xk. And then I take this straight line and solve the equation represented by the tangent dash line, where the line intersects the x-axis that will be my next guess, xk plus 1. The idea is actually rather simple. That is actually how I remember the actual formula. Let's just derive this formula, and you see it takes only a moment. We know the slope of this line of f prime of k, and which are also equal to the y distance here over the x distance. And the y distance here is f of xk, and the x distance here is xk minus xk plus 1. And I shall equal to f at xk prime. Rearrange terms here and solve this equation and with respect to xk plus 1, and we immediately get the following. It is xk plus 1 equal to xk minus f of xk over f prime of xk. We see that if we want the Newton's method to work well, and one would need to assume that f prime very close to r or exactly at it shall be not 0. Otherwise, the denominator goes to zeros and the method gets into trouble. So this will be the formula that we will be working with for a while Newton's iteration. Now we look at an example using Newton's method to find approximations to some quantity. Here is the problem. I want to find a numerical method to compute the square root of a and test your method for a equal to 3. It was a fancy description of the problem. Actually, you see that square root of a root for the function, a quadratic polynomial, that is x squared minus a. We can throw in Newton's method for finding roots for this function. Newton iteration will be the following. Xk plus 1 will be xk minus f of xk over f prime of xk. Plug in your actual function f, which is xk squared minus a. F prime is 2xk. And with a little bit simplification, you get x over 2 plus a over 2xk. Let's test this on a equal to 3. We know square root of 3 is approximately 1.7. Let's choose an initial guess to be a good one, because that is important to Newton's convergences. If your initial guess is good, x0 chosen to be 1.7. We will now run some iterations. So x0 is 1.7, and we listed the error on the right, which is about 7.2 times 10 to the negative 2. Next, I run other 3 iterations. We can check the error, and now it's 10 to the negative 16. This is extremely fast convergence. Next, we will look at the second method. We see that in Newton's method in the iteration, one needs to compute f at xk as well as f prime at xk. So 2 function evaluations, and one can argue that sometimes f prime of x might not be available or might be very difficult to compute. So we would prefer to avoid that computation. And this leads to the next method. A way to avoid computing f prime is to use some kind of approximation. If we already have computed xk and xk plus 1, we can simply take the slope of the secant line connecting the 2 points at xk and xk plus 1, and use that as an approximation to the derivative of f at xk. In a way, we are approximating the function f by the secant line through xk and xk minus 1, and then we will solve this linear function, and that root will be the next approximation x at k plus 1. And that is why this method is called the secant method. So plug in this f approximation for the secant method. Now reads the following. It's basically Newton, but the f prime is approximated by this expression. We see that in order to initiate the iteration, we now need 2 initial guesses, x0 and x1, but that should not be a problem. If you have a good initial guess, x0, you can choose the nearby point x1 and initiate the iteration here. Now let's look at the same example as we did with Newton's method. Let's say we want to compute the square root of a, and we try to solve the polynomial x squared minus a equal to 0 by second method. If you set it up, then this becomes the second iteration. It is similar to Newton, but the f prime is replaced by the approximation xk minus xk minus 1 over f at xk minus f at xk minus 1. After some simplifications, we can get the expression. We are going to test this with a equal to 3. We choose initial data which is similar to Newton's method. Let's say x0 is 1.65 and x1 is 1.7. They are good initial guesses. So x1 is 1.7 and its error is shown in the right here. After other 4 iterations, the error reduces down to 10 to the negative 15. We see that the convergence actually is a little bit slower than Newton's method, but really not much. If you counted the total number of iterations needed here, it's only 1 more than that we did for Newton's method. From conclusions, what we learned? In numerical analysis, Newton's method, also known as the Newton-Raphson method, is a root-finding algorithm which produces successively better approximations to the roots of a real-valued function. The second method can be thought of as a finite difference approximation of Newton's method. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,